Hello everyone, I'm Jiameng. I am a PhD student at Virginia Tech. Today I will present my work on detecting deepfake images. First of all, what are deepfakes? Deepfakes are synthetic media produced using deep generative models. This includes multiple modalities like images, videos, audio, text. In this work, we focus on deepfake images. Deepfakes can be easily generated today. You don't need much technical expertise. There are services that allow you to perform controlled generation of deepfake images. On this website, you can even specify gender, age, ethnicity for the headshots you need. Keep in mind that none of these people actually exist. They are all generated by a machine learning algorithm. So what can go wrong? A bad actor can use them to create fake social media profiles, fake pornography, and disinformation campaigns. In fact, Facebook recently removed accounts that used AI to create fake profile pictures. Deepfakes can be a threat beyond the web as well. Our recent work showed how one can create medical deepfakes. A bad actor can use deepfake techniques to translate a healthy chest X-ray into a fake image that indicates signs of a specific disease, thus triggering misdiagnosis by doctors. Now, before we go further, it's important to understand how deepfake images are created. The most popular approach is to use a generative adversarial networks, or a GAN. A GAN, in short, is a pair of deep neural networks, a generator and a discriminator that learns in tandem to synthesize high-quality images. Recently, GAN research has made significant progress. You can see the photorealistic images produced by StyleGAN proposed in 2019. It is even hard for a human to differentiate between deepfake and real images. So this makes it a serious threat. In this work, we propose a new approach to detect deepfake images among other real images. First, let's understand the limitations of prior work. One approach is to train a supervised DNA classifier to detect deepfakes, but it can be hard to obtain a large representative training dataset of deepfakes. Plus, these methods may have poor generalization performance, which means they perform poorly when applied to previous unseen deepfakes. We could also apply anomaly detection schemes to spot semantic inconsistencies in the image by analyzing high-level content. However, the quality of GAN-generated images has been significantly improved today. Besides, both above approaches are prone to issues of bias as they analyze high-level image content. Given these limitations, we propose a deepfake detection scheme called NoiseScope. Given a test set of images, NoiseScope aims to identify fake images. NoiseScope is blind, in that it doesn't assume a priori access to any fake images or knowledge of the generative scheme used to create them. It only requires a set of real images used for calibrating detection parameters. NoiseScope is thus also agnostic to the type of GAN used and works for any type of high-level image content. NoiseScope is inspired by prior work in camera fingerprinting, or image forensics, which shows that camera devices leave unique noise patterns or fingerprints in images due to device imperfections. Given a camera image, you can suppress the high-level image content to obtain a noise residue, and this noise residue contains a unique and stable fingerprint pattern that can be used to identify the camera or the source of the image. This raises the natural question: do GANs leave fingerprints as well? The answer is yes. We observe a stable noise pattern in fake images as well. But are there any difference between camera fingerprints and model fingerprints? Here are some examples. This row shows camera fingerprints. It might be hard to see the patterns, but if we look closely, there are patterns here. Now, when we look at model fingerprints, you see a very different pattern. there are checkerboard artifacts in all these model fingerprints. This can be attributed to the deconvolutional layers of GANs. We leverage this difference between model and device fingerprints to identify model fingerprints in a blind setting. Before we go further, let me explain how we can extract fingerprints from images. To do this, we need a set of images from the same source, be it camera or model. Next, for each image, we extract the noise residue which suppresses high-level content. We can then average these residues to cancel out random noise, leaving us the final fingerprint for the model or the camera. Once we have a model fingerprint, it is easy to detect fake images from that model. Given a model fingerprint F and a test image, we can compute the correlation between the fingerprint and the noise residue of the image, R. If the correlation is above a certain threshold, the image is fake. Otherwise, it is real. Now, the key challenge is in extracting these model fingerprints in a blind setting. It is a challenge because first, you cannot extract fingerprint from a single image. You need multiple images from the same source, as you saw earlier. And second, in a blind setting, you have no a priori access to fake images to build a model fingerprint. To overcome this, NoiseScope extracts available fingerprints from the test site itself in an unsupervised manner. Now, let's get into understanding the NoiseScope detection pipeline. In the first step, we extract the noise residues for each image in the test site. The second step is to extract any available fingerprints, be it model or device, from these residue images. From step 1, we have a set of residues. We start by grouping residues that have a high correlation into clusters, as they are likely come from the same source. However, it is hard to directly group residues, as they contain random noise that affects correlation. To address this challenge, we propose an incremental clustering strategy to group residues. Successive steps will merge the clusters based on correlations between the cluster's fingerprints, which are simply the average of the cluster members. The clustering process stops when no more clusters can be merged based on a correlation threshold. We thus end up with a collection of fingerprints. These fingerprints can belong to a model or a device, so our next step is to identify that. In the third step, we separate device fingerprints from model fingerprints. Recall that model fingerprints tend to have a distinct checkerboard pattern. Therefore, we develop a machine learning classifier that looks for anomalous texture patterns to identify model fingerprints. Finally, we take the model fingerprints and compute their correlations with all the noise residues of test site images. If the correlation is higher than a pre-calibrated threshold, then the image is fake. Next, let's look at detection performance of NoiseScope. We conducted extensive evaluation covering multiple datasets and GANs. This table shows the F1 score of detecting deepfake images. NoiseScope consistently achieves high F1 score above 90% and also outperforms the best existing blind detection scheme, labeled in the table as CSD-SVM. CSD-SVM analyzes disparities in the color components between real and fake images. We also compared NoiseScope with a well-known supervised approach, Mesonet. We took Mesonet and trained it on fake images from StyleGAN. Next, we prepared two testing sites, one containing StyleGAN fake images and another containing PGGAN fake images. Turns out, Mesonet fails to generalize to PGGAN fake images or previously unseen image distributions. But when we apply NoiseScope, it consistently performs well on both datasets. It's also important to evaluate NoiseScope against an adaptive attacker. We evaluated a range of countermeasures targeting different components of NoiseScope pipeline. I will talk about two of them here. One approach to evade detection is to disrupt the fingerprints via image compression, which is well studied in the image forensics literature. But NoiseScope is resilient. Compressions still leave artifacts in the noise space that NoiseScope can easily identify. Another countermeasure is to spoof the fingerprint to be from a specific camera. NoiseScope can be made resilient by using multiple filters while extracting the noise residues. Moreover, aggressive spoofing against multiple filters will significantly degrade the image quality, thereby rendering the attack unsuccessful. In addition to this, we looked at a lot more evaluation by building different test sites, such as imbalanced test sites with few fake images, test sites with fake images from multiple GANs, and so on. For countermeasures, we considered a couple of other post-processing schemes that are commonly used in prior work to disrupt fingerprints, including gamma correction, histogram equalization, adding noise, etc. For attacks that degrade the performance, we recommended effective recovery schemes against them. You can check out our paper for detailed evaluation results. To conclude, we believe blind detection is a promising research direction as it compensates for the poor generalization performance of supervised approaches. And insights from the mature field of digital image forensics are useful to detect deepfakes. Now we are working on extending NoiseScope to detect deepfake videos. Our code is available at GitHub. Thanks so much for listening.